So the Fast and the Curious, graphing campus walkways.
So these are our slides, our group, what is our project, where our data come from, calculations, implementation, running algorithms, and then what we learn.
So first off, our group. So this is me, Carlos Salazar.
I'm Emiliano Gonzalez.
So our project, campus walkway graph. So what we wanted to achieve was basically finding the shortest path from building to building. This is kind of like our base for our project. So we modeled our college campus as a graph. Our nodes were key locations, so like the church, the library, dining hall, Dante, Garaventa, all of those buildings. And then our edges are physical walkways between the buildings themselves. And so essentially the goal of our project was to analyze the shortest path across campus.
So where did our data come from? We got our data physically walking the walkways between campus locations. While we walked those walkways, we collected two data points. The first being steps taken, which we counted in our head and then recorded in a document. And then the time taken, we used the timer app on our phones to time like the amount of time it took in seconds from each location walkway. And then we use these to estimate the cost of each edge.
So yeah, our calculations. So this is how we calculated our edge weight. We balanced both our physical effort and the time efficiency that it took to reach one building from another. So this ensured that our shortcuts were truly short by more than just distance. So this is the formula we use. So our edge weight is equal to our time in seconds plus our steps, and this is all over two.
So our implementation of the graph. So how do we implement the graph? So we use Network X and Python to build and visualize the graph. Nodes were the locations, like we mentioned earlier, and edges were the walkways with the weights. We implemented the data that we collected into a list with each item as like a dictionary. So the to and from location, and then the keys were like their like ex locations, so like the church or the library, and then the time was like another item in the dictionary, and then its key would be like the seconds. This is our final graph. As you can see, it's not exactly like the exact locations that it would be on campus, but it's still like in correlation with like how to get from one place to another and like the proper like edge way. So from the soda center, you can walk to the credit union pavilion and it has an edge way of 201.5. You can go from the soda center to the bookstore is another example, and so on. So yeah, this was our first snippet of the code. So this is the list that I mentioned earlier, and this is the dictionary within the list. There's the different items in it. So the from, and then it's keys. So like the Cafe Louis, Oliver Hall, all the different locations. And then to is like where we were going to. And then the key would be like the other location, the steps and seconds, and then, or sorry, the steps and like the amount of steps you took, and then the time in seconds after that. And then the second part of our code was where we actually like created the graph. And we also where we put in our for loop, which has the calculation for the formula for the weight. And then as you can see here, in the for loop at the top is where we calculate it. And then under that is where we print out like the actual walkways and the weights. And it prints it out in the terminal so we could just double check that like it was like doing the correct calculations. And then an example that we use under that would be like the source, the library, and then the target, the soda center, finding like the shortest path between those two. And yeah, so running algorithms.
These are the different algorithms that we kind of took into account when it came to our project. So we used Dijkstra's algorithm to find the shortest paths. So the fastest route from the rec center to the credit union pavilion. And then we tried other algorithms like the Bellman Ford for comparison and the Floyd Warshall. Um,
Yeah, and then when we ran the algorithms, when we put like the same like target and source, for example, recreation center to the credit union pavilion, it gave the same like results for each algorithm. So it was correct. There was nothing wrong with the graph, and like it kept like and reinforcing that we all the algorithms were running perfectly fine. And then on the right are different results. I was gonna put in the same source and target, but I wanted it to be like different ones, so then we could like look at the differences. So for the first one was the Bellman Ford results from the Recreation Center to the chapel, and it gave back Recreation Center to Garaventa Hall, passing Dante Hall, then Oliver Hall, and then lastly you get to the chapel, and the total weight's 177.50. And then the dice reversal is the Recreation Center to the Credit Union Pavilion. So you see Recreation Center, past Garaventa Hall, past Dante Hall, past Oliver Hall, past the chapel, past Brousseau Hall, and then you finally get to the Credit Union Pavilion. And then the Floyd Warshall was the distance from Citro Hall to Dante Hall. And this algorithm actually didn't print out like the path, but it printed out the total weight, which was 144.50. So like out of all like the algorithms, I'd say like the Bellman Ford was like the best one for us because it printed out like the path and the total weight as well. And we just use like pre-made like references of like the algorithms using like Network X. It already had like the library for and like the different like variables for the algorithms. So what we learned in conclusion, real world graphs require thoughtful data collection modeling. Weight choices affect algorithmic outcomes significantly, and graphs can be used in tools and analyzing many world problems in various fields such as transportation, ecosystems, etc. Thank
Thank
you.
you.